let's get started with the electron numerical relativity. And I guess the very first question that we should answer is, what is numerical relativity actually? So if I was in person, or if it was easy to speak up, I would actually ask this question to the audience, and the organizers, do you give me the okay to do that? So especially in the beginning now, I think I would like to have it a bit interactive. So what do you think numerical relativity is?
Somebody should speak up.
So,
It's a numerical tool to study the Einstein equation. I mean, to evolve systems in general relativity.
That's right. Yeah. So, and more broadly, it's the idea that you can model the nonlinear regime of gravity in general relativity. So, for Einstein's equations or extensions thereof, in 3+1 dimensions or more. And typically, we use high-performance computing facilities to do that. Now, the other question, and I'll take some ideas and then start with my notes actually. Where do we apply numerical relativity? So what are the science cases that you can think of?
Evolutions of binary black holes, binary neutron stars, or even isolated compact objects.
Yeah.
And I mean, where strong gravity is.
Yeah, so these are the obvious one and really the traditional science driver. Can you think of anything else?
Boson stars.
Boson stars, yeah. So that goes into the realm of what I would call testing gravity and testing prediction of gravity. What else can we think about?
Even modified theory of gravity, or.
Yeah, I see Tanasa, two participants raising their hands. So if you can speak up, that would be great. So Tanasa first, and then Pranav.
I've heard we can apply it in aerodynamics.
Yeah, so I think we are not applying it so much in aerodynamics, but there you would also have numerical models. That's correct. Pranav?
Gravitational lensing, etc. things which in which we can use the numerical relativity to kind of simulate the trajectories and orbits of the, let's say, massless and massive particles.
Yeah, that's right. So let me just throw out a few other applications out there. So one, for example, is cosmology. So I know that people are developing numerical relativity codes to look, for example, for inhomogeneous inflation. And the field of numerical cosmology is something that I've seen grown over the last few years. When I started out my PhD, we actually looked at black holes in high dimensions. So again, strong field gravity, but beyond our standard model in 4 dimensions or 4-dimensional asymptotically flat spacetimes. There are applications where people look at asymptotically anti-de Sitter spacetimes in the context of the gauge gravity duality, which has been really hot for a few years and is still a very interesting topic. I also see applications in mathematical relativity. So if people start studying the nonlinear stability of spacetimes, of high-dimensional spacetimes, that's another place where we apply numerical relativity. So even though gravitational wave source modeling is extremely rich and the main science driver, the tool has many more applications. And I just wanted to point that out to you, how broad the tool this actually is. Okay, so with all that said, today I will actually focus on the gravitational wave science driver. So I will talk about numerical relativity in 3+1 dimensions for Einstein's equations without a cosmological constant and an asymptotically flat space.
I have a question from Tanasa.
Yeah, do we have a question? Please go ahead.
Yeah, when you said we can apply it to more than 3+1 dimension, what did you mean by that?
So there are theories of gravity that suggest that we may live in a high-dimensional spacetime. So that was really hot about 10 years ago when people were thinking about Randa-Sundrum models. So by basically trying to explain why we have this huge discrepancy in the cosmological constant, and they were trying to suggest models with high dimensions where the fundamental Planck scale would be of the order of TeV. And if you remember these notes about, you may find black holes at the LHC, so that is essentially behind that people were looking at high dimensional gravity theories. And what we have done back then is to take these high dimensional theories and write them down with a lot of symmetry so that we could use our 3+1 dimensional numerical relativity codes to study them, right? And some of these theories are quite interesting from a theoretical perspective because the type of black hole solutions that you find are much broader and so there's much more phenomenology than you have in 4 dimensions.
Mm-hmm. Thank you.
Yeah. Okay. Good. So with all that, let me start my notes here, and I will share my screen. So start now, and you should be able to see this. Good. Yeah. So as I said, I will use my tablet to take notes and to write the lecture. I took the liberty to already write down a couple of textbooks. If you're interested to learn more about numerical relativity, there's Alcubierre's textbook, Introduction to the 3+1 Numerical Relativity. Then Thomas Baumgarten and Stu Shapiro have actually 2 textbooks. One is like really dense and has a lot of information in detail. And they recently put out a textbook for beginners for numerical relativity, which is a good starting point, especially for students who want to learn the basics. And so they will have a first contact with the topic. And then Masaru Shibata also has a very nice textbook on numerical relativity, where he actually covers, everything from numerical relativity in 4 dimensions. And he also talks about high dimensional spacetimes or some of these modified gravity theories that were already around at the time. And of course, there are a lot of there's a lot of online material and living reviews and lecture notes that I haven't put here extensively. If you can think of your favorite, please feel free to share that in the chat with the rest of the group. Okay, good. So, but with that, let me just start here. So we already addressed the question, what is numerical relativity? So let me just very briefly remind you. So that's essentially solving Einstein's equations. And let me abbreviate Einstein's equations as EEs or extensions, if you want to think about beyond GR series, typically in 3+1 dimensions, and typically using high-performance computing facilities. And the goal is to model, to simulate the nonlinear regime of gravity. Yeah, this is important. And since we already extensively talked about the application in gravitational wave source modeling, let me just very briefly remind you. So here we had the science cases, and one of the main one, of course, is gravitational wave sources. And if I think about typical binary evolution, where the gravitational wave signal would cover the in-spiral merger, where we have nonlinearities, and then the ring down. So here we would have our black holes or neutron stars, compact objects in general, very far apart. So the velocities involved here would be rather small. Gravitational field is weak. And here we would use post-Newtonian theory. Then we have the regime where gravity is really nonlinear, and we can no longer resort to these simplifications. And so we really need to solve Einstein's equations numerically. Here we would have velocities of the order of the speed of light. We would use numerical relativity, and here we really cover the non-linearities of the theory. And then, of course, we have the ring down here. Let me just try to illustrate this like so, where our black hole that formed through the merger settles down to just a single rotating black hole described by the Kerr solution if we are in general relativity. So here, this is the ring down. Typically employ perturbation theory. Or we can also capture this part with numerical relativity. And actually, for me, if I develop a new code, if I want to study a specific extension of GR or specific new model, then I would actually use this merger ring down part or even just perturbations and try to compare to perturbation theory where I have that available as a benchmark for my numerical implementation. Okay, good. So just as a little bit of a roadmap and outline for this talk, I will just give you an idea of what are the theoretical ingredients that I need in order to do these simulations. So if you say, oh, I come to you and I want you to model, I don't know, two Bose stars, since we are one of the audience that was brought up, how would you go about doing this starting from scratch? Right. So what you want to do first, obviously, so let's see. Yeah, and so what are the ingredients? And as I said, so this is a little bit of
Helvi, there's a question from.
Yes, of course. Yes, please go ahead.
Hi, Helvi. This quick question. Would you say that just the velocity would be sufficient indicator of the absence of nonlinearity, or should we have densities or some other things to indicate something like the density of matter? Yeah, I guess.
Right. So here I was thinking about small velocities and small gravitational fields. Right.
Oh, I see.
Yeah. So I didn't write this down explicitly. Let me actually maybe write this down here as well. So if I take the gravitational field to be small as well.
Small. Yeah.
Yeah, in the appropriate sense, let me put it like this. Then yes. And then of course, you know that if you have a neutron star binary, at least a leading order, if you neglect finite size effects, you would just model those as point particles, right? And then of course, going beyond that approximation, you would take into account finite size effects.
Mm-hmm. All right. Yeah, thank you.
Oh, but that's a very good point, because I said it, but I didn't write it down. Yeah. Okay, so yeah, what do we need in terms of ingredients? And as I said, so this is a bit of an outline of what I want to discuss today. And also, if you ever want to come back to this lecture and say, okay, now I want to read more about this, what do I actually need? You can come back here to check this. So the very first one, especially if I think about extending general relativity, or is of course the theoretical model. It may seem obvious, but let me just spell it out. So today, as I said, we want to look at Einstein's equations in vacuum. I will not talk about matter simulations today. I will focus on four-dimensional spacetimes that are asymptotically flat. Yeah. So what we will model, or what we will talk about today, is really just Einstein's equations. So we have the Einstein tensor here, Ricci tensor -1/2 metric times the Ricci scalar equals to 0. Good. So second, we need to, or most numerical relativity codes use a decomposition of the space-time into spatial hypersurfaces that are evolved in time. So this will be the next part, the space-time decomposition. That is, we will make the space and time dependence explicit. Yeah, and as you will see, this will provide us with a set of kinematic equations. Yeah, so think about the analogous of the kinematic equations that you have Newtonian gravity, for example, or not in Newtonian physics. we will get equations for our positions or our metric and our time derivative of the metric, which will be the extrinsic curvature. Yeah, so in the classical mechanics example, that would be the equivalent to positions and momentum. Good. So once we have that, we will actually, let me just go to the next slide. Once we have that, which is a very generic decomposition, we will actually apply this to the Einstein's equations, or more generically, you would perform a 3+1 decomposition of your field equations, which give you the dynamics. So 3+1 or space-time decomposition of the field equations. As I said, in our case, this will be Einstein's equations. And that gives you the dynamics of the space-time. So these are typically hyperbolic type PDEs. So PDEs, partial differential equations. And you typically also get a set of constraint equations. And those are of elliptic type. So these are elliptic, that is time-independent partial differential equations. Good. So these are the evolution and constraint equations. Of course, you also, if you have a time evolution formulation, then you also need to prescribe initial data. So what values do your fields take on the initial time slice? So that's the next part of initial data. That is, if you think about it, this will be your metric and the time derivative of your metric at your time slice that you label as t=0. Yeah, and this will be determined by the physical system that you want to consider. So, for example, what I will talk about today will be one example of a single black hole or binary black holes. But of course, then that can be much more general. And what we will see is that we actually we will have to make some assumptions that are guided by the physical system that we want to study. And we also need to solve these constraint equations, which are 4 coupled elliptic partial differential equations. Yeah, so we need to solve the constraints. And as I already said, so at least in 4 dimensions, these are 4 coupled elliptic PDEs. This is our initial data. Then we need to think about a bit more about our actual evolution system. And here are questions about, for example, well-posedness. So is the system of partial differential equations that I'm writing down actually mathematically well-posed? That is, if I start with some smooth, unique initial data, do I still have a unique solution at late times that is bounded by my initial data? And in numerical relativity, this mathematical property is important because it's a necessary condition for numerical stability. So if our equations or our system of equations are not well-posed, then any small perturbations, numerical perturbations in our evolution can grow exponentially and essentially destroy our evolution. Yeah, so that's why we need to care about this as well. And so it well-posed initial value problems. And essentially that will boil down to slightly rewriting the equations that we find in the 3+1 formulation. Also need to think about gauges and our coordinate evolution, and how we treat, if we study black hole spacetimes, how we treat the black hole singularity, because again, computer doesn't like divisions by 0 or infinity, so we have to understand how to treat these physical singularities properly be able to evolve the system. And then lastly, once you have all of this theoretical work, you also you want to think about the observables that you actually want to extract from your numerical simulation, right? So these would be, for example, gravitational. So let me be more generic, wave extraction. And here you can either think about Newman-Penrose formalisms, which is what most of the numerical relativity codes are using, or metric perturbations, which gives you the strain more directly. You also want to understand or measure horizons. Typically, we use a local measure called apparent horizon, because event horizon, to measure event or to calculate the event horizon, you need to know your entire space-time. So this can be done, but it's much more costly. So we typically look at apparent horizons. And similarly, it's for local measures of our black hole. Good. And that's a theory. And then, of course, there could be an entirely different lecture on all the numerical implementations that you could think of. I will not talk about this here unless you ask me about this later, and I can give maybe just a very brief taster for that. So what I want to do today is to touch on some of these topics. Let me just highlight those. So I will obviously talk about, let me just go to the previous slide. So I will obviously talk about the space-time decomposition. Oops, sorry about that. So space-time decomposition, this will be the first part today. I will talk about the 3+1 decomposition of Einstein's equations. And this is, by the way, where we have our extensor tutorial next Monday. Yeah, so we will also see how you would do this calculation explicitly using extensor. And I will talk about a little bit of well-posedness and different evolution schemes. So this will be item 5 here. And we will talk about initial data. And if you have time, can briefly touch on choices for the gauge. Yeah, so that's the plan for now, and then the second lecture later this afternoon. So with all that said, let me just pause for a moment, because this was all very generic, but if you do have any pressing question now, just interrupt me. While I'm going down here. Okay, so I don't see anything here. I don't see anything in the room. So I will just continue. And we will talk about what I labeled as part 2, the 3+1 decomposition of space-time. And here, the idea is that even though having our beautiful, elegant, four-dimensional description of space-time for numerical relativity is actually useful to make the space and time dependence of our quantities explicit. Yeah, so we will more mathematically, we will foliate our four-dimensional space-time manifold into space-like hypersurfaces that are level sets of quantities. So these hypersurfaces, space-like hypersurfaces, will be parameterized by a time parameter t. Yeah, so we foliate our four-dimensional space-time manifold. Let me call this M with some metric G into space-like hypersurfaces. And let's label those as capital sigma with some three-dimensional spatial metric gamma, parameterized by this time parameter t. Yeah. So we would decompose our manifold into these hypersurfaces. Oops. Sorry, times r. So I apologize about the background noise. I hope it's not too bad. More specifically, if I wanted to illustrate that, what we will do is to take our manifold and we foliate that into these hypersurfaces. Let me just draw them in 2 dimensions. Let me suppress the 3rd dimension to make the drawing a little bit more easy and visible. Yeah, so these would be our hypersurfaces, sigma, say, t. And the next one would be sigma of t plus some delta t. So our time parameter would go up here in this direction. And now the first question that we need to ask ourselves is actually, how would we propagate a point, say, from our hypersurface sigma t to the next hypersurface sigma plus delta t? And to do this, we can actually define the following quantities. So the first one that we will use, that we will define for us, is the normal vector, nu. And let me just, for illustration purposes, actually put an arrow on here. So this is the n is a normal vector, so the vector normal onto the hypersurface. It's a time-like vector. So nu is our normal time-like vector with a normalization nu equals -1. Yeah, good. And I should also, okay, this was not very clever. So I should also say that on our hypersurface here, I already indicated the spatial metric gamma ij. So on our hypersurface sigma, we have the induced spatial metric gamma ij. And let me just put here the notation. So my Greek indices all run from 0 to 3. So they are space-time indices. My Latin indices, I, J, and so on and so forth, run from 1 to 3. So they are spatial indices. And now that we have the metric, we can actually measure proper distances on our hypersurface as follows. That we say we may have a line element, say dl squared, which is gamma ij dxi dxj if x mu are our coordinates and xi are the spatial coordinates. Good. So this is our metric and normal vector, and now we will want to be able to describe, as I said, this propagation of a point from one hypersurface to the next. So we will introduce 2 quantities. One quantity is a lapse function that basically describes how much proper time elapses between the hypersurfaces. So that would go along the direction of the normal. So here we would have the lapse function alpha times the normal vector, and I will write this down on the next slide. I just want to finish the developing the graphic first. This is our lapse function, and then, as you can see, if you follow an observer along the normal, we actually end up here. So to describe the displacement or the shift that we have for the point between the point that we get by just following the normal observer to the actual point is what we call the shift vector. So let me take green here. So this would be the shift vector that describes this relative displacement here. So this is a shift. And now if we want to construct the time vector going from point P to point P prime, that would be given by the lapse function times the normal vector plus our shift vector here. Good. Yeah, and let me just write down briefly lapse and shift on the next slide for completeness. Yeah, so as I said, we introduced the lapse. In numerical relativity, we typically call it alpha. If you have a more analytic background, you may also be familiar with the notation of using capital N and Ni for lapse and shift. So these are the same quantities. Yeah, so the lapse alpha is a proper time. That elapses between hypersurfaces measured by an observer moving along the normal. And the shift vector beta I gives you, actually to be more precise, not just the displacement, but the relative velocity between the normal observer and the lines of constant spatial coordinates. And by construction, the shift vector and the normal vector are orthogonal. So we have beta mu n mu equals to 0. Yeah, so that's why I'm actually jumping between beta I and beta mu. So where I need to be explicit about beta being four-dimensional, like here, I will use my four-dimensional indices. Otherwise, I will resort to the three-dimensional ones. Now that we have all the ingredients to describe our space-time in 3+1 dimensions, let me just write down the metric, the four-dimensional metric, in terms of this quantity. So our metric, four-dimensional metric, in terms of our three-dimensional metric, gamma ij, lapse and shift, is given as follows. So our line element would be this, if in 4 dimensions, g mu dx mu dx nu, and we can write this as minus, and then the tt component is alpha squared minus beta I contracted dt squared plus the 0 I components would be 2 gamma ij beta I, and then we have dt dxj, and then the purely spatial components are determined by the spatial metric gamma ij dxi dxj. Good. Couple of notes are in order here because our three-dimensional spatial metric also defines a projection operator, and to see that, let's actually write down the relation between this induced metric, which it really is, and the four-dimensional metric. So we can also write this as follows, that if I take the space-time indices on our induced metric, if I take gamma mu nu, then this would be our space-time metric g mu nu plus normal vector n mu n nu. Yeah, and again, the signs here are chosen such that the normal vector is time-like and our metric, induced metric, is space-like. And as I was about to say before, so gamma ij, or this induced metric, defines a projection operator Yeah, so we would have gamma now with upper index mu, lower index mu equals, and let me take delta to indicate our identity matrix for, the matrix for the four-dimensional spacetime, and then we have plus n mu upper index, n mu lower index. And now you can, if you want to take a four-dimensional vector, you can identify its purely spatial components and its normal components by the following decomposition that you say. So let's just take vector, let me call this v mu, and we can write this as a component n times the normal vector plus, let me take this kind of curly v here, mu, where the normal component is calculated from the contraction of the full vector with the normal vector. And the second part here is a spatial component. So here we have the projection with our projection operator gamma I mu acting on our full vector. And this is actually something that we will use later on, and we will apply this kind of projection to derive our Einstein's equations in this 3+1 formulation. Good. Before we can go there, however, we also need to introduce a quantity that describes how our hypersurface is embedded in our four-dimensional spacetime. And this is described by the extrinsic curvature. So this will be our next item. And enough space here. Yep, so that works. So the next item that we, or the next quantity that we need to introduce is called extrinsic curvature. We typically use k mu nu as a symbol to describe it. And let me just start with a geometric interpretation of this extrinsic curvature, which I think is usually a little bit more illustrative. So imagine you have a spacetime, and let me just suppress two dimensions and just, hypersurface. So let me suppress two dimensions. So assume we have something like so. And we look at the normal vector here, and now we look at the parallel transport of this normal vector to a different part of our hypersurface. So we'd have this here. So the extrinsic curvature is a measure for the change in your normal vector. So it's essentially defined as the gradient of the normal vector. Yeah. So in geometric terms, the extrinsic curvature is defined as minus, we have a projection here, kappa mu, and then we have the gradient nabla, which is the four-dimensional covariant derivative, kappa acting on our normal vector mu. Let me just highlight the sign here. So this is a convention. If you look at Wolf's book, he usually uses a plus convention here. So we use this convention to indicate that our time slices are future directed. Yeah, good. And with a few lines of algebra, you can actually show that the extrinsic curvature k mu nu is related to the Lie derivative of the induced metric along the normal vector. So what you will find is that this will be minus 1 over 2 alpha times the Lie derivative along the normal vector of the induced metric. And if you if you insert what we derived before for the time vector, and do some rearrangement, you can actually show that the extrinsic curvature can be related to the time derivative minus a Lie derivative along the shift vector of the induced metric. And this is a definition that you are likely to find in most numerical relativity books. But there is this nice relation between the geometric interpretation of this extrinsic curvature and its meaning as a time derivative as kind of the momentum or a second fundamental form of the metric. Yeah, and if you rearrange this equation, you will see that the extrinsic curvature, or if you want to calculate the time derivative of the 3 metric, and let me write it in this form, partial t minus a Lie derivative along beta acting on the induced metric, that is minus 2 alpha times the extrinsic curvature. And here we have our first evolution equation, which is a kinematic equation. Yeah, and remember I was saying before that what we will find at the end of the section is indeed a time derivative, a time evolution equation for the metric, and this is a kinematic. So this kind of decomposition, if you can apply this to your space-time, you will always find this kinematic relation. Yeah, so it does not tell you anything about the dynamics of the space-time yet. So for that you would need the field equations and need to decompose those. Just one more comment before I continue doing precisely that actually a very similar formulation has been developed by Arnold and Miesner, and they were looking for a Hamiltonian formulation of the metric and their conjugated momenta. So the conjugated momenta can be related to this extrinsic curvature that we are seeing here. And they introduced that to try and find a canonical formulation of gravity to quantize gravity. So that was the idea behind it back in the day. So if some of these look familiar to you from a completely different context, then that's why. And in fact, the equations that we will derive next, which are the constraint and an evolution equation for the extrinsic curvature in numerical relativity, are often called the Arnold-Miesner equations, even though they're not exactly in the form that was originally derived. Yeah. And in this, as the last point, so in this canonical formulation, the lapse and the shift are actually the Lagrange multipliers in this Hamiltonian formulation. So I think it's like a really nice side note and something to keep in mind. Okay, so let me just take a couple of questions, if you have any, before I actually talk about the 3+1 split of the field equations. Are there any in the room? I don't see anything in the chat here.
No raised hands anywhere, it seems. Anybody has a question? I think there's a quiz at the end, right? So.
No.
Ask now.
Okay, so I don't see anything. I will just continue. And if you do have any questions at any point, just interrupt me.
I'll just ask something stupid if you don't mind. So is it true that the Lie derivative along the normal vector as an operator is just this difference between dt and Lie derivative along the this L beta?
So you would have. So can you say that again?
I mean,
so
the equality between, so you have this equality between Ln, the Lie derivative along the normal vector, equals the difference between the time derivative and the spatial data derivative, not the displacement derivative. These are
exactly.
And equal as operators, right? I mean, you don't. It's true for anything. You don't have to apply just the metric.
No. So I mean, what I did here was simply to say, okay, if you go back to our decomposition that I've written up previously, right? I can relate the time vector and the normal vector as I have done here in blue. So I essentially just use this relation.
So what I'm saying is that these two operators are just the same. It's not just.
They are just the same, right? But I'm writing this out because what we want to do in numerical relativity is. So we evolve quantities in time. So what we want to do, the way we want to write down the equations is to have something like time derivative of our objects equals stuff on the right-hand side. So yeah, you're right. So they are equivalent, but we will, so in practice, we use this explicit time derivatives. That's why I've rewritten this.
Thanks.
Does that make sense to you?
Yeah, no, thank you.
Yeah, and in fact, so even though this is equivalent, deciding what the lapse and the shift are in your evolution can actually make or break this evolution, right? So it's actually quite important. Okay. Good. So yeah, let's talk about the 3+1 decomposition of Einstein's equation. And just a quick question, since we started a little bit late, do you want me to stop on, well, not on the hour, but at 45, or do you want me to continue for a couple of minutes more?
My little thing says it's another 13 minutes or so left, so just, I mean, take your time, we have plenty of space, plenty of time.
Yeah.
We're running into the orientation. That's the only thing.
Yeah, exactly. So what I have in my schedule is running this until
So you want
45 and then have a second part later on.
50 is fine, but not later than that.
Yeah, so let's say take another 13 minutes or so.
Okay, good. Okay, yeah, so as I said, now talk about the next part. So what we've derived so far are our kinematic equations. So essentially what I'm doing in my current undergrad course, Physics 101, the equivalent would be just writing down the kinematic equations for position and velocities. So now we actually want to get the dynamics in. And for gravity, for Einstein's gravity, that means we want to decompose our field equations into this space-time form. So in a set of evolution equations and constraint equations. And actually, sorry, this should be in my, to be consistent with my previous numbering. This should actually be 3 here. The 3+1 split of the field equations. Okay, yeah, and as I just said, this is what will give us the dynamical description for our theory. And we will see this part again on Monday. It should be the 20th of September, where we will look at X tensor for the decomposition. So here I will just give you the equations without going into any of the details of how to derive them. And just as a reminder, so download the notebook, and the link should be available on the program. If you want to have a hands-on session, and also install X tensor. Yeah, and the website to do so is very simple, so I can remember even without writing it down. So it's xact, so xact.es. And that's a free package. So this is what we're going to use. Okay, so if we want to make the space-time split of Einstein's equations explicit, what we will need are the projections of the Riemann tensor, and Ricci tensor and Ricci scalar into the 3+1 dimensional quantities. We will need the projections of the energy momentum tensor. And then once we have those two, we can finally do the projection of the Einstein's equations. So the first thing that I will write down, without going into the details of any derivation, is actually give you the relation between the four-dimensional, not going to give you the relations explicitly, but we do need relations between the four-dimensional Riemann tensor and the three-dimensional one. So the first one, they are called Gauss-Kodazzi relations. And this will give you a relation between the four-dimensional Riemann tensor and the three-dimensional one. And one thing in terms of notation, if you think about the covariant derivative in 4 dimensions, I will use nabla, a symbol for that, and then in 3 dimensions, I will use a capital D to indicate the covariant derivative, which is a projection of our 4-dimensional covariant derivative here. So this is very schematic. Yeah, good. Also, and again, yeah, so what we would also need would be the projection of the energy momentum tensor if we wanted to go beyond vacuum spacetimes. And actually, maybe I can just write this down explicitly as an example. So if you say you have your energy momentum tensor T mu nu, then you have 3 types of independent projections. So the first one would be the projection of the energy momentum the contraction of the energy momentum tensor with a normal vector in both indices. And this would give you an energy density. And this is very generic. So in fact, the way we have implemented that in the code is that in our evolution code, so for those of you who are using or want to use the Einstein toolkit, we would actually implement these very generic forms to be read in our metric evolution SORN or module. And then the definition of what this rho and what the energy momentum tensor actually are is defined in the meta evolution SORN. So if you wanted to couple a perfect fluid, you could do that. If I'm, if I'm coupling scalar fields or massive scalar fields or massive vector fields to my evolution equations, then I have a very similar structure that I define this in a separate module that is then read into the metric evolution SORN, so that we have this very general structure for the metric evolution and can couple to different types of matter very easily. So this was the energy density. Then I can also think about a mixed projection. So contract one of the indices with a normal vector and project the other one onto the onto the hypersurface, sorry. Yeah, so here we would have, say, rho nu. Let me project the first index, mu rho, and contract the second, and nu, minus sign here. So this would give us the energy momentum flux. And yeah, I got the indices right. Yeah, and of course, by symmetry, you would get the other projection as well. And then the last one is a spatial stress tensor. And here I'm projecting both indices of my energy momentum tensor with our projection operator, so induced metric. So here we have upper index rho, lower index mu, and then gamma, upper index sigma, lower index nu, so that we get the spatial stress tensor as mu nu. Yeah, and very similarly, we do precisely such a projection of the Einstein's equations as well. So again, we will look at all the independent projections that we may have. So let's look at the first one, or the first set, where we contract our Einstein's equations with a normal vector in one or both indices, and that actually gives us the constraints. So if I go up here.
Probably just a heads up, about less than 5 minutes left.
Mm-hmm. Say again, sorry?
Less than 5 minutes left.
Okay. That would be enough time actually to do this. So as I said, we will now look at the decomposition of Einstein's equations, or these projections. Yeah. So the first set of equations that you will get is a Hamiltonian constraint. And here we are constructing Einstein's equation. And let me just focus on the vacuum Einstein's equation. So just the Einstein tensor with our normal vectors, typically actually at a factor of 2 in here, that's equal to 0. And if I write this out in terms of my 3-dimensional quantities, then I have the 3-dimensional Ricci scalar here minus the extrinsic curvature Kij plus the trace of the extrinsic curvature squared. Yeah, so this is our first constraint, our Hamiltonian constraint. The second part, if we contract one of the indices with a normal vector, we will get the momentum constraint. Yeah, and here again, called MI, we will have the contraction of the projection of one of the indices with our metric, contraction of the other one with a normal vector. We write this out as basically as a divergence of the, oops, let me just do it in this form, divergence of the extrinsic curvature minus the derivative of the trace of the extrinsic curvature equals to 0. And these are constraint equations that we would try to solve for the initial data. And I will stop here, and we will just write down the evolution equations in the second part of the lectures today. So let me stop here and take any questions that you may have at this stage.
Thank you so much.